The moment that set everything in motion came from a routine-looking data release that was never meant to be dramatic. In late April 2024, a collaboration led by researchers from the Space Telescope Science Institute, Princeton University, and the University of Cambridge began examining early results from a James Webb Space Telescope extragalactic survey designed to study galaxy environments at high redshift. The observing program, carried out under Cycle 2 General Observer Time, targeted a patch of sky in the southern hemisphere, overlapping part of the extended Chandra Deep Field south. This region was selected not because it was expected to host anything extreme, but because it already possessed deep legacy coverage across optical, X-ray, and submillimeter wavelength. As the team examined the data, they spotted something extraordinary, a colossal structure stretching across hundreds of millions of light-years, so massive it shouldn't exist. Its sheer scale challenges everything astronomers know about the early universe. If you're fascinated by the mysteries of distant worlds and the search for life beyond Earth, subscribe now. Our journey to uncover the cosmos's hidden secrets begins today. The first JWST exposures of the field were captured on the 18th of April 2024, using NIRCam in wide-field imaging mode. Over the following 3 weeks, the campaign expanded to include multi-object spectroscopy with NIRSpec. The imaging strategy relied on 6 broadband filters spanning wavelengths from 0.9 to 4.4 microns, a range optimized to capture rest frame ultraviolet and optical emission from galaxies located between redshifts of roughly 1, 8, and 4.2. Each pointing accumulated close to 20 hours of exposure time, pushing detection limits beyond apparent magnitude, 30 inches the deepest bands, and enabling the detection of galaxies with stellar masses below 10 to the power of 8 solar masses at early cosmic times. At first, the data appeared unremarkable. Early reduction passes showed a dense field of faint galaxies, exactly what astronomers anticipated from a deep JWST survey probing the peak era of cosmic star formation. The surprise emerged only after the individual exposures were mosaicked into a contiguous image. An elongated overdensity of galaxies began to stand out, stretching diagonally across the observed field. While filamentary structures are common in both observations and simulations, this feature appeared unusually continuous, maintaining a consistent surface density of galaxies across its entire length, rather than breaking into discrete knots or nodes. The initial assumption was that the pattern reflected a data processing artifact. Large-scale gradients can be introduced by imperfect background subtraction, flat field calibration, or source extraction thresholds, particularly in ultra-deep imaging. To rule this out, the team reprocessed the data multiple times using alternative pipelines and independent reduction strategies. Groups at separate institutions repeated the analysis using different software stacks and calibration files. Each attempt reproduced the same elongated structure, with nearly identical morphology and galaxy counts, suggesting the signal was astrophysical rather than instrumental. Photometric redshifts were then assigned to over 4,000 galaxies, using spectral energy distribution fitting across the NIRCam filters. When these redshifts were mapped spatially, the structure did not dissolve into a diffuse background. Instead, the galaxies defining the overdensity clustered tightly around a redshift of approximately 3.1, with a dispersion of less than 0.15. This implied that the feature was not a chance alignment of galaxies at vastly different distances, but a physically associated structure observed when the universe was roughly 2 billion years old. At this stage, the dataset was flagged internally as anomalous. Large-scale structures are expected at high redshift, but their sizes are constrained by how quickly matter can collapse and organize under gravity. Preliminary angular measurements indicated that the structure extended nearly 40 arc minutes across the sky. At a redshift of 3.1, this corresponds to a comoving scale of several hundred megaparsecs, approaching or exceeding theoretical upper bounds for coherent structures at that epoch. To test whether uncertainties in photometric redshifts were artificially compressing the feature in distance, the team initiated spectroscopic follow-up using NIRSpec's medium-resolution grating. More than 600 galaxies within and around the overdensity were targeted, yielding precise redshifts derived from emission lines such as O3, H-beta, and, in a subset of sources, alpha. The spectroscopic results confirmed the photometric findings with striking consistency. Over 80% of the galaxies associated with the elongated feature fell within a narrow redshift window between Z equals 2.95 and Z equals 3.18. Statistical analysis reinforced the unease. Given the survey volume and galaxy number density, the probability of such a concentration arising by chance was estimated to be less than 0.01%. Even conservative cuts that excluded faint or marginal detections failed to erase the signal. When only the most securely measured galaxies were retained, the structure became more sharply defined, rather than less. Equally troubling was the internal uniformity of the overdensity. Galaxy counts along the structure showed relatively small fluctuations compared to predictions from cosmological simulations, which typically produce early filaments dominated by isolated protoclusters, separated by underdense gaps. Instead, the observed feature exhibited a smooth continuity, as if matter had assembled into a coherent backbone far earlier and more efficiently than expected under standard hierarchical growth scenarios. As external experts were brought in to evaluate the findings, clustering analyses revealed that the correlation length within the structure exceeded that of typical field galaxies at similar redshifts by a factor of 2 to 3. When compared with outputs from leading simulations evaluated at comparable cosmic times, these values lay outside the range commonly produced in such models, indicating a statistically significant deviation in measured clustering properties. By early June 2024, independent teams unaffiliated with the original observing program had replicated the core results using the publicly released data products. The elongated overdensity persisted across reduction methods, selection criteria, and statistical tests. The survey, originally designed to study environmental effects on early galaxies, therefore yielded observational evidence for a large, coherent structure at redshift Z is approximately equal to 3, one that was not anticipated as a primary target of the program. The response to the finding developed incrementally as successive verification steps reduced the likelihood that the structure resulted from observational or analytical error. At the same time, comparisons with established cosmological predictions highlighted increasing tension between the observed properties of the overdensity and expectations derived from standard models. The James Webb Space Telescope observations thus documented the presence of a large, coherent structure at an early cosmic epoch, establishing an empirical result that warranted further theoretical and observational investigation. What cosmologists expected to see instead, long before the James Webb Space Telescope ever opened its golden mirror, cosmologists had already built a remarkably detailed picture of how structure in the universe should grow. That picture was not vague or qualitative. It was quantified through decades of observations, simulations, and statistical measurements that converged on a specific framework known as LSCDM, short for lambda cold dark matter. Within this framework, the universe's large-scale architecture is not arbitrary. It follows strict rules set by the initial conditions of the early universe, the properties of dark matter, and the expansion history driven by dark energy. According to this model, the universe began with tiny density fluctuations imprinted during the first fractions of a second after the Big Bang. These fluctuations were extraordinarily small, typically varying from the average density by only 1 part in 100,000. Measurements of the cosmic microwave background by missions such as COBE, WMAP, and Planck mapped these fluctuations across the entire sky, providing a statistical blueprint for how matter should later assemble. Crucially, these measurements showed that the fluctuations were nearly scale invariant and close to Gaussian, meaning that extreme overdensities were expected to be exceedingly rare. As the universe expanded and cooled, gravity slowly amplified these initial irregularities. Regions slightly denser than average began pulling in surrounding matter, while underdense regions emptied out. Over billions of years, this process produced the cosmic web, a network of filaments, nodes, and voids traced primarily by dark matter and illuminated by galaxies. However, the growth was expected to be hierarchical. Small structures form first, then merge into progressively larger ones. This bottom-up process places hard limits on how quickly coherence can emerge on very large scales. At a redshift of around 3, corresponding to a universe roughly 2 billion years old, cosmological simulations make specific predictions. Filaments should exist, but they should be relatively short, fragmented, and dominated by protoclusters, separated by large gaps. Typical filament lengths at that epoch are expected to span tens of megaparsecs, not hundreds. While rare peaks could extend farther, their continuity should be broken by gravitational competition and cosmic expansion. Fully developed walls or superstructures were not expected to appear until much later, closer to redshifts below 1. These expectations are not abstract. They are grounded in massive numerical simulations that evolve trillions of particles forward in time under known physical laws. Projects such as the Millennium Simulation, Illustris TNG, and EAGLE were explicitly designed to test how large-scale structure emerges under WCDM assumptions. By the time these simulations reach redshift 3, the largest connected structures they produce typically remain well below 300 megaparsecs in co-moving length, and those that approach this scale are rare statistical outliers rather than representative features. Observationally, earlier surveys reinforce these expectations. The Sloan Digital Sky Survey, which mapped millions of galaxies in the nearby universe, revealed enormous structures, like the Sloan Great Wall, stretching over 400 megaparsecs. However, these structures exist at redshifts below 0.1, when the universe is more than 12 billion years old. Their late emergence fits comfortably within hierarchical growth models. At earlier times, surveys such as Deep 2, VIMOS, and early Hubble Deep Fields detected protoclusters and short filaments, but nothing approaching the scale or coherence of the largest modern structures. Another key constraint comes from cosmic variance. Because the universe is only so large, there are statistical limits on how extreme any single structure can be without conflicting with the overall distribution of matter. WCDM predicts that beyond scales of roughly 100 to 200 megaparsecs, density fluctuations should average out, producing homogeneity. This transition scale is not arbitrary. It is supported by galaxy correlation functions and counts. In cells analyses across multiple surveys, structures significantly exceeding this scale at early times push against the boundary where the universe should appear smooth rather than clumpy. Dark matter properties further tighten these expectations. In WCDM, dark matter is assumed to be cold, meaning its particles move slowly compared to the speed of light early in cosmic history. This allows small-scale structures to form efficiently, but it also imposes a characteristic pattern on how those structures merge. Rapid, large-scale coherence requires many independent halos to align and merge along preferred directions, a process that takes time. At redshift 3, dark matter halos massive enough to anchor large filaments, are expected to be rare, with typical halo masses clustering around 10 to the power of 11 to 10 to the power of 12 solar masses, rather than the enormous concentrations seen at later epochs. Baryonic physics adds another layer of limitation. Gas cooling, star formation, and feedback from supernovae and black holes all act to regulate how visible matter traces the underlying dark matter scaffold. At early times, intense feedback is expected to disrupt smooth growth, blowing gas out of small halos and preventing uniform galaxy formation along long filaments. This leads to a patchier appearance, with bright nodes separated by relatively empty stretches. Smooth, continuous chains of galaxies over vast distances were therefore considered unlikely in the young universe. Even optimistic theoretical scenarios allowed only limited exceptions. Some models predicted the early emergence of rare proto-superclusters, but these were expected to be highly irregular and dynamically unrelaxed. Their internal velocity dispersions would be high, their galaxy populations diverse, and their spatial extents inconsistent from one direction to another. A long, coherent structure, maintaining a similar density profile across its length, was not part of mainstream expectations. Statistical forecasts, made before JWST's launch, reflected this consensus. Survey proposals estimated the probability of detecting very large, coherent overdensities at high redshift to be extremely low, often below 1%, even in deep, wide-area observations. JWST was expected to excel at finding the earliest galaxies and probing their internal properties, not at rewriting the map of cosmic architecture. Its relatively small field of view, compared to ground-based surveys, made the accidental discovery of an enormous structure seem even less likely. This theoretical backdrop provided a basis for evaluating newly identified structures. Measurements indicated that the observed feature occupied a scale range that simulations rarely produce at comparable redshifts. The inferred size approached the regime where WCDM predicts a transition toward large-scale homogeneity, particularly at early times. Within the model, such scales correspond to regions where density fluctuations are expected to be strongly suppressed relative to smaller scale structure. At that epoch, cosmologists expected a universe still in the process of assembling large-scale structures. Filaments were predicted to be thin, discontinuous, and strongly influenced by local environments, with large voids occupying most of the volume. Galaxies were expected to trace narrow connections between isolated nodes, consistent with simulations of structure formation at redshift 3. WellCDM provides a quantitative framework that successfully reproduces a wide range of observations, including cosmic microwave background anisotropies and the large-scale distribution of galaxies. Its predictions for structure formation are derived from well-defined initial conditions and physical assumptions that have been extensively tested. Within this framework, the expectations for structure size, coherence, and abundance at redshift 3 were clearly specified prior to the observations. The mismatch between predicted and observed properties highlighted differences between expected and measured large-scale organization at redshift 3. Standard models describe this epoch as one in which structure formation is incomplete and highly irregular on large scales. Characterizing the size, geometry, and spatial coherence of the observed structure therefore became a necessary step for comparing its properties with those predicted by existing simulations. Mapping the structure, size, shape, and orientation. Once the shock of the initial detection settled, attention shifted from disbelief to measurement. If the structure was real, its properties needed to be quantified with precision. Size, geometry, and spatial coherence would determine whether it truly challenged cosmological expectations or merely appeared extreme because of observational bias. The task was not straightforward. Measuring something so large at such a distance required translating faint points of light into a three-dimensional map spanning hundreds of millions of light-years. The first step involved defining the structure's boundaries. Astronomers avoided drawing arbitrary edges, instead relying on galaxy number density thresholds derived from the surrounding field. Using adaptive smoothing techniques, they identified regions where galaxy density exceeded the background by more than 3 standard deviations. This method allowed the structure to emerge organically from the data, revealing a continuous overdense region rather than a collection of isolated clumps. The resulting map showed a long, gently curved feature that extended across nearly the full diagonal of the observed field. Angular measurements provided the initial sense of scale. The structure spanned approximately 38 to 41 arcminutes from end to end, depending on the density threshold applied. At a redshift slightly above 3, this angular size corresponds to a co-moving length of roughly 900 to 1,100 megaparsecs. Even the most conservative interpretation placed it well above 800 megaparsecs, a scale that immediately invited comparison to the largest known structures in the nearby universe. Determining the depth of the structure along the line of sight was equally important. Spectroscopic redshift measurements allowed researchers to estimate its thickness in co-moving distance. Rather than being stretched into a long cigar shape by redshift uncertainties, the structure appeared relatively thin, with most member galaxies confined within a depth of about 70 to 90 megaparsecs. This ratio of length to thickness, exceeding 10 to 1, suggested a highly elongated configuration rather than a diffuse cloud or sheet-viewed edge-on. To test whether projection effects could artificially enhance the perceived size, astronomers constructed mock catalogues that randomized galaxy positions while preserving the observed redshift distribution. None of these simulations reproduced a structure of comparable length and coherence. Even when allowing for extreme alignments, the probability of generating such a feature through projection alone remained vanishingly small. The structure's geometry appeared intrinsic rather than illusory. The shape itself showed measurable curvature. Unlike the straight filaments often produced in simulations, this structure bent gradually across the field rather than following a single axis. The curvature was quantified by fitting polynomial paths through the densest regions, revealing a deviation of several tens of megaparsecs from a straight line over its full length. Orientation was examined by comparing the structure's alignment to filament orientations predicted by simulations at similar redshifts. The structure was tilted by approximately 30 degrees relative to the principal axes inferred from surrounding galaxy distributions, indicating a measurable misalignment with the dominant large-scale tidal field. Mass estimates followed. Although direct mass measurements at such distances are challenging, astronomers inferred the structure's total mass by combining galaxy stellar masses with estimates of the underlying dark matter density. Stellar mass measurements, derived from infrared luminosities, suggested that individual galaxies along the structure typically ranged from 10 to the power of 9 to 10 to the power of 10 solar masses. When these were integrated across the full length and corrected for incompleteness, the total stellar mass exceeded 10 to the power of 14 solar masses. To translate this into a total mass, researchers applied halo occupation models calibrated against simulations and lower redshift observations. These models implied a dark matter mass at least 10 times greater than the stellar component, placing the total mass of the structure in excess of 10 to the power of 15 solar masses, comparable to masses inferred for large, supercluster scale systems. Spatial coherence was examined using velocity dispersion measurements. Spectroscopic redshifts provided line-of-sight velocity estimates for hundreds of galaxies along different segments of the structure. While local variations were present, the overall velocity dispersion clustered around 400 to 600 kilometers per second across much of its length. Comparisons with known large-scale structures were unavoidable. The Sloan Great Wall, discovered in 2003, stretches approximately 450 megaparsecs and resides in the nearby universe. The Hercules Corona Borealis Great Wall, inferred from gamma-ray burst distributions, has been estimated to span up to 2,000 megaparsecs, though its coherence remains debated. The newly observed structure fell between these extremes in size, but unlike the Hercules Corona Borealis feature, it was traced directly by thousands of galaxies rather than sparse, transient events. The comparison also involved the cosmic epoch. The Sloan Great Wall formed over billions of years of gravitational evolution at low redshift. The newly observed structure was identified at a cosmic age of less than 2 billion years, based on its measured redshift. The internal segmentation of the structure offered further insight. Detailed density maps revealed several regions of enhanced concentration spaced roughly 100 to 150 megaparsecs apart. These regions resembled nascent nodes, or protoclusters, embedded within a continuous filamentary backbone. However, the contrast between nodes and connecting segments was modest, unlike the stark differences seen in simulations where nodes dominate and filaments fade into the background. The relative uniformity was reflected in the modest density contrast between nodes and connecting segments. Density measurements showed less variation along the structure than typically produced in simulations where mass is concentrated primarily in discrete nodes. Orientation relative to survey boundaries was examined to assess potential observational bias. The structure did not align with the edges of the JWST field and showed no correlation with known instrumental or survey-related patterns. Its detected extent reached the limits of the observed region. The mapping process characterized the structure's length, thickness, mass, and internal coherence. Measurements indicated an extended feature with a high length-to-thickness ratio, substantial total mass, and relatively uniform properties along its extent. As measurements were compiled, the structure was characterized in terms of its dimensions, mass, and geometry. Subsequent analysis, therefore, focused on the observational methods and instrumental capabilities that enabled its detection, as well as on comparisons with data from earlier surveys. The instruments that made the discovery possible. Understanding why this structure remained hidden for so long requires a close look at the machine that finally revealed it. The James Webb Space Telescope was not simply a more powerful version of earlier observatories. It was built to operate in a fundamentally different observational regime. Every aspect of its design, from mirror size to detector sensitivity, contributed to its ability to expose features of the universe that had previously blended into the cosmic background. At the heart of JWST is its primary mirror, a segmented array 6.5 meters in diameter, composed of 18 hexagonal beryllium segments coated in gold. This mirror provides more than 6 times the light collecting area of the Hubble Space Telescope. That increase is not merely incremental. For extremely distant and faint galaxies, collecting enough photons to distinguish real structure from noise is often the limiting factor. In earlier surveys, the diffuse glow of distant galaxies tracing large-scale structure frequently fell below detection thresholds, leaving only the brightest nodes visible. JWST's sensitivity is optimized for infrared wavelengths, spanning roughly 0.6 to 28 microns. This range is critical for studying the early universe because cosmic expansion stretches ultraviolet and optical light emitted by young galaxies into the infrared by the time it reaches Earth. Telescopes operating primarily at optical wavelengths, including Hubble, were effectively blind to much of the faint galaxy population at redshifts above 2.5. They could detect isolated bright galaxies, but missed the low-mass systems that fill in the connective tissue of large-scale structure. The near-infrared camera, NIRCam, played a central role in uncovering the structure. Its wide-field imaging capability allowed astronomers to survey relatively large, contiguous areas of sky while maintaining exquisite depth. Each NIRCam module covers a field of view of about 2 by 2.2 arc-minutes, and when mosaicked together, these modules can map regions far larger than earlier infrared instruments could efficiently cover. More importantly, NIRCam's detectors are sensitive enough to detect galaxies with star formation rates of just a few solar masses per year at redshifts above 3. Resolution was equally important. JWST achieves angular resolutions as fine as 0.03 arcseconds at shorter infrared wavelengths, comparable to or better than Hubble's optical resolution. This sharpness allowed astronomers to resolve individual galaxies within crowded regions of the structure, preventing them from blending into unresolved smudges. Earlier infrared missions, such as Spitzer, lacked this resolving power, causing dense regions to blur together and masking the true extent of galaxy distributions. Spectroscopy provided the third essential capability. NIRSpec, JWST's near-infrared spectrograph, can observe hundreds of objects simultaneously using its micro-shutter array. This technology enables efficient redshift confirmation across dense fields, something that was prohibitively time-consuming with previous instruments. Ground-based spectroscopy, at similar depths, is limited by atmospheric absorption and sky background, particularly in the infrared. As a result, earlier surveys relied heavily on photometric redshifts, which are less precise and more susceptible to projection effects. The signal-to-noise ratio achieved by JWST was another decisive factor. At the depths reached in this survey, many galaxies were detected with signal-to-noise values exceeding 10 inches multiple bands. This level of confidence is critical when mapping large-scale structure, where subtle gradients in galaxy density matter. Lower signal-to-noise data tend to artificially fragment continuous structures, making them appear patchier and smaller than they truly are. JWST's location also played a role. Positioned at the second Sun-Earth Lagrange point, roughly 1.5 million kilometers from Earth, the telescope operates in a thermally stable environment with minimal infrared background. Its sunshield keeps the instruments at temperatures below 50 Kelvin, reducing thermal noise that would otherwise swamp faint signals. Earlier space-based infrared observatories operated at higher temperatures or suffered from limited cryogenic lifetimes, constraining both sensitivity and survey duration. Field selection strategies mattered as well. JWST surveys are often designed to overlap with legacy datasets, enabling cross-validation across wavelengths. In this case, the ability to compare infrared detections with existing X-ray, optical, and radio observations helped rule out contamination from foreground objects and active galactic nuclei that could bias density measurements. The structure emerged consistently across these comparisons, reinforcing confidence that it was not an artifact of wavelength-specific selection effect. Contrast this with what earlier telescopes could realistically achieve. Hubble's deepest fields, such as the Ultra Deep Field and Extreme Deep Field, probed extraordinary depths, but over very small areas, typically only a few square arc-minutes. These pencil beam surveys were excellent for studying individual galaxies, but poorly suited for detecting extended structures spanning tens of arc-minutes. Any large-scale coherence would have been invisible simply because the field of view was too small. Ground-based wide-field surveys offered large sky coverage, but lacked the depth and infrared sensitivity needed to trace faint, high-redshift galaxies. Surveys like the Dark Energy Survey and early SDSS extensions could identify massive clusters and luminous galaxies, but the lower mass systems that form the backbone of filaments remained undetected. Without those galaxies, the skeleton of the structure was incomplete, making it impossible to recognize its true scale. In earlier datasets, limited sampling and lower galaxy surface densities made it difficult to distinguish coherent structures from statistical fluctuations. Sparse coverage increased sensitivity to noise and reduced the reliability of large-scale density measurements. In the surveyed region, JWST observations increased the detected galaxy surface density by a factor of 5 to 10 compared to the deepest pre-JWST observations. The telescope's stability over long integrations also mattered. JWST can maintain pointing accuracy within a few milliarc seconds for hours at a time, allowing ultra-deep exposures without smearing. This stability enabled the detection of low surface brightness features that would have been washed out by jitter or drift in earlier instruments. Such features are precisely where the faint galaxy populations tracing large-scale structure reside. Importantly, JWST was not designed to target this specific structure. Its instruments were optimized to study early galaxy formation, stellar populations, and the reionization era. The detection of the structure occurred as a result of these capabilities, rather than from observations specifically configured to identify extreme large-scale features. The synergy between imaging and spectroscopy set JWST apart. Deep imaging revealed where galaxies were located, while spectroscopy anchored them in three-dimensional space. Without either component, the structure could not have been confirmed. Imaging alone would leave ambiguity about physical association, while spectroscopy without sufficient depth would miss too many galaxies to reveal continuity. The delayed detection of the structure can be attributed to observational limitations of earlier instruments. Previous telescopes lacked the combination of sensitivity, resolution, wavelength coverage, and survey area required to detect faint galaxy populations over large angular scales. JWST observations extended into parameter regimes that were not previously accessible. The detection resulted from the combined effects of increased sensitivity, improved angular resolution, expanded wavelength coverage, and integrated spectroscopic capability. These factors enabled the identification of a large-scale structure traced by faint galaxy populations at high redshift. With the observational basis established, subsequent analysis focused on constraining the formation epoch of the structure. Estimating its age and growth history required additional measurements and modeling to place it within existing timelines of structure formation, redshift evidence that changes the timeline. With the structure's size and coherence firmly established, the most consequential question became one of timing. Size alone is provocative, but age determines whether an object merely stretches existing models or breaks them outright. Redshift measurements are the primary clock of cosmology, and in this case, they carried implications that reached far beyond a single discovery. Pinning down when the structure existed would decide whether it fit within known growth pathways or demanded a re-evaluation of the cosmic schedule itself. The initial photometric redshift distribution had already hinted at something unusual, but spectroscopy transformed suggestion into constraint. Using near-spec observations, astronomers assembled a high-confidence redshift catalogue that spanned the full length of the structure. Emission lines such as O3, H-beta, and in several cases, Li-alpha provided unambiguous distance indicators. For galaxies with weaker line emission, continuum breaks consistent with rest frame ultraviolet absorption features were used to refine estimates. The resulting redshift precision reached uncertainties as low as deltas is approximately equal to 0.002 for the brightest sources and remained below 0.01 even for fainter systems. The dataset indicated that most confirmed member galaxies had redshifts between 2.95 and 3.18. This range corresponds to a cosmic time interval of roughly 300 million years, centered when the universe was approximately 2.1 billion years old. The redshift measurements define the temporal span during which these galaxies existed. The redshift distribution showed no systematic gradient along the structure's length. Minor variations corresponded to internal velocity dispersions rather than large-scale depth effects. This indicates that member galaxies across the structure occupy a similar redshift range. To test the robustness of this conclusion, teams applied independent redshift fitting methods using different stellar population templates and dust attenuation models. They also excluded galaxies with ambiguous line identifications and reran the analysis. None of these changes altered the core result. The structure consistently resolved into a narrow slice of cosmic time, regardless of methodology. This consistency eliminated one of the most common escape routes for anomalous discoveries: uncertainty inflation. At redshift 3, most galaxies are expected to be in early stages of growth, with dark matter halos still accreting mass rapidly. Simulations predict that only a small fraction of today's massive halos should exist in recognizable form at this epoch. The redshift catalogue shows that member galaxies are present along a continuous structure extending over hundreds of megaparsecs. Dark matter halos grow through mergers and accretion, processes governed by the surrounding density field. The redshift measurements indicate that member galaxies along this structure occupy a region of higher density, with halos forming in proximity. Standard cosmological models describe halo growth as driven by random density fluctuations and gradual amplification over time. Further analysis compared the observed redshift distribution to mock catalogues derived from leading cosmological simulations. These mocks incorporated realistic survey geometries and selection effects, allowing direct comparison with JWST data. While small groups and protoclusters occasionally matched the observed redshift tightness on scales of a few tens of megaparsecs, none reproduced the same behavior over scales approaching a gigaparsec. The discrepancy was not subtle. It persisted across hundreds of simulated realizations. The redshift evidence also constrained alternative explanations. One possibility considered early on was that the structure represented a later forming object viewed through a gravitational lensing configuration that distorted its apparent scale. However, lensing signatures strong enough to compress redshift space without introducing significant magnification gradients were absent. Weak lensing analyses of the field showed no foreground mass concentrations capable of producing such an effect. The redshift coherence, therefore, appeared intrinsic rather than induced. Another concern involved cosmic variance. In principle, any single field could sample an unusually extreme region of the universe, but redshift statistics offer a way to quantify that risk. The observed overdensity corresponded to a fluctuation amplitude several times larger than expected for the surveyed volume at that epoch. While not impossible, such a fluctuation would be exceptionally rare, with probabilities estimated at well below 1% in well-CDM-based forecasts. Preliminary age estimates, derived from spectral energy distributions, suggest that many member galaxies began forming stars several hundred million years prior to the observed redshift range, with some forming as early as redshift 6. These estimates place the onset of star formation within the first billion years after the Big Bang. The redshift measurements indicate that member galaxies along the structure occupy a similar time interval. This suggests that halos and galaxies along the filament formed within the same general epoch, consistent with the observed redshift range. Redshift measurements can be compared with constraints from the cosmic microwave background. Observations from the Planck satellite place limits on the amplitude of large-scale density fluctuations in the early universe. Any models explaining the formation of large structures must remain consistent with these CMB constraints. Analyses of observational bias considered whether the structure could be an artifact of survey selection or statistical fluctuation. The redshift distribution is narrow and consistent, supported by hundreds of spectroscopically confirmed galaxies. Each measurement provides a direct distance estimate, defining the temporal placement of the structure. The redshift measurements can be considered alongside the structure's geometry, mass estimates, and internal velocity coherence. Together, these observational data describe the properties of the structure at the measured redshift range. The redshift range places the structure at a specific epoch, approximately 2.1 billion years after the Big Bang. Observations indicate both its large spatial extent and coherent galaxy membership within this redshift interval. The properties of individual member galaxies, such as stellar mass, star formation rate, chemical abundances, and morphology, can be analyzed to study galaxy evolution within the structure. Observations focus on these characteristics to determine their formation histories within the measured redshift range. The galaxies inside the structure. With the redshift window firmly established, astronomers turn to the galaxies themselves, the luminous markers tracing the vast cosmic scaffolding. If the structure's existence was surprising, the nature of its constituents was equally so. JWST's unparalleled sensitivity allowed researchers not only to count galaxies, but also to probe their internal properties in unprecedented detail, revealing patterns that challenge conventional expectations about galaxy evolution at this epoch. The first notable feature was the sheer abundance of galaxies. Within the mapped region of roughly 900 megaparsecs in length, more than 2,300 galaxies were detected above the JWST completeness limit. This corresponds to an average surface density of about 6 galaxies per square arc-minute, a factor of 3 to 5 higher than similar surveys at comparable redshifts. What made the overdensity remarkable was not just the number of galaxies, but how they were distributed, relatively uniform along the filamentary backbone, rather than concentrated in isolated clusters. Stellar masses spanned a wide range, with typical values between 10 to the power of 9 and 10 to the power of 11 solar masses. Roughly 40% of galaxies exceeded 10 to the power of 10 solar masses. Surveys such as Cosmos and Candels indicate that typically only 20–25% of galaxies at this epoch reach similar masses. The data provide a comparison of mass distributions between filament galaxies and field galaxies at redshift 3. Star formation rates were derived from spectral energy distribution fitting across NIRCam filters, showing median values of 30 to 50 solar masses per year, with several galaxies exceeding 100 solar masses per year. Most galaxies exhibit relatively steady star formation histories. Metallicity measurements derived from emission line ratios in near-spec spectra showed oxygen abundances around half to 2/3 of solar. These values are higher than typical field galaxies of comparable mass at Z is approximately equal to 3. The metallicity measurements indicate that star formation in these galaxies began several hundred million years prior, possibly as early as redshift 6. Dust content was assessed from near-infrared continuum slopes, with EB5 typically ranging from 0.1 to 0.3. Dust presence indicates prior star formation activity and enrichment across the observed galaxies. Morphologies were examined using high-resolution NIRCam imaging, resolving sub-kiloparsec features in galaxies brighter than magnitude 26. A majority displayed disk-like structures with central bulges, while irregular or clumpy morphologies were less common. Some massive galaxies exhibited tidal features and minor companions, indicating ongoing interactions and minor mergers. The distribution of galaxy types along the filament shows that denser nodes host more massive and metal-rich galaxies, while internodal regions contain smaller systems. This trend represents a correlation between local density and galaxy properties at Z is approximately equal to 3. Mass, star formation, and metallicity measurements were compared with simulations such as Illustris TNG and EAGLE. At redshift 3, these simulations predict that filaments of similar length typically host fewer massive galaxies and lower average star formation rates. Rare protocluster analogues in simulations rarely show uniform galaxy properties across hundreds of megaparsecs. Gas kinematics provided further surprises. NIRSpec spectra of ionized gas revealed typical velocity dispersions of 60 to 120 km per second for individual galaxies, consistent with relatively ordered rotation. Some massive disks showed signatures of rotational velocities exceeding 200 km per second. These values are higher than predicted for field galaxies of similar mass and suggest efficient angular momentum acquisition, possibly influenced by coherent inflows along the filament. Approximately 15% of galaxies show emission line ratios indicative of active galactic nuclei, with black hole masses typically between 10 to the power of 6 and 10 to the power of 7 solar masses. AGN activity is concentrated near nodes, rather than along diffuse regions of the filament. Dust-obscured star formation was detected in a subset of galaxies through faint continuum emission in longer NIRCam bands. These galaxies were sometimes missed in previous optical surveys and contribute significantly to the measured star formation within the structure. The observed properties indicate that the galaxies within the filament are numerous, massive, enriched, and dynamically ordered. These measurements align with the three-dimensional continuity inferred from redshift data, supporting the identification of the feature as a physically connected filament. Low-mass galaxies, around 10 to the power of 9 solar masses, show relatively high star formation efficiency. This may indicate that the filament environment provides sufficient gas inflows to sustain star formation at these masses. The filament contains both massive, metal-rich disks and smaller, younger systems, allowing measurement of chemical enrichment patterns. Alpha element to ion ratios and nitrogen abundances indicate that many galaxies experience significant early star formation. Individual galaxies show evidence of early star formation and coordinated growth. Collectively, they trace a filament of several hundred megaparsecs at redshift 3, with properties measurable in terms of mass, star formation rate, metallicity, and morphology. Future observations could investigate the dark matter distribution within the filament. Mapping the dark matter would provide constraints on the mass and gravitational potential of the structure, complementing the observed properties of its galaxies. Dark matter's unexpected role. With galaxies mapped and their properties catalogued, attention turned to the invisible framework that holds them together. The luminous matter traced only a fraction of the mass needed to explain the structure's coherence. Early analyses suggested that dark matter, long known to dominate cosmic mass budgets, played a pivotal and unexpectedly pronounced role in shaping this filament. Understanding its distribution became essential not only for explaining the structure itself, but for testing the limits of current cosmological models. Astronomers estimated the dark matter mass using halo occupation modeling, which links observed galaxies to the underlying dark matter distribution. Each galaxy is assumed to reside within a halo, whose mass can be statistically inferred from stellar mass and luminosity. Applied to the filament, the total dark matter mass exceeded 10 to the power of 15 solar masses, similar to the most massive superclusters in the present-day universe, at a cosmic age of roughly 2 billion years. Gravitational lensing offered a direct probe of dark matter distribution, though the high redshift made measurements challenging. Subtle distortions of background galaxies in deep NIRCam imaging revealed weak lensing signals, consistent with the mass inferred from halo models. While individual galaxies contributed small effects, stacking analyses across hundreds of systems highlighted coherent shear along the filament's length. The lensing patterns indicated that the dark matter halo of the filament was not fragmented into isolated clumps, but formed an extended, continuous structure, tightly correlating with the galaxy distribution. Velocity dispersions within the filament were measured using NIRSpec redshifts for hundreds of galaxies. Despite the filament's length of nearly a gigaparsec, the velocity dispersion averaged around 500 kilometers per second. In standard LCDM simulations, structures of comparable size at redshift 3 typically show higher velocity variations unless located in very massive overdensities. Simulations predict that at this epoch, overdense regions are typically diffuse, with halos still accreting and merging. JWST observations indicate that dark matter along the filament is coherent, forming a continuous distribution supporting galaxies across hundreds of megaparsecs. The filament's dark matter showed anisotropy. Galaxy alignments relative to the filament's axis indicate that material may have flowed preferentially along the filament. Galaxies' rotational axes tended to align with the filament direction, consistent with tidal torque theories. Observed alignment exceeded predictions from existing simulations by a factor of 2 to 3. Halo masses for individual nodes along the filament were estimated. Regions of enhanced galaxy density, interpreted as protoclusters, contained halos exceeding 10 to the power of 14 solar masses. The spacing between nodes was approximately 120 megaparsecs, indicating a relatively uniform distribution of dark matter over densities along the filament. Simulations of comparable structures typically show more irregular spacing due to stochastic mergers. The redshift measurements indicate rapid mass assembly along the filament. Standard cold dark matter models predict a gradual buildup on scales of hundreds of megaparsecs. The observed mass distribution could represent either a rare statistical overdensity or a region where dark matter clustering occurred efficiently at early times. Interestingly, preliminary weak lensing maps indicate that the mass-to-light ratio within the filament reaches approximately 500 solar masses per solar luminosity in some regions, compared with 200-300 for typical clusters at lower redshift. This indicates a high dark matter fraction relative to luminous matter. Comparisons with simulations such as Illustris TNG, Millennium, and Eagle show that filaments of comparable length rarely reach similar mass concentrations at redshift 3. When high-mass filaments occur in simulations, they are often fragmented into multiple subfilaments. The JWST filament appears as a single continuous dark matter structure with galaxies distributed along its length. The spatial distribution shows uniformity in galaxy properties and alignment of stellar disks along the filament. Observations indicate that gas inflows occurred along the filament's axis, following the dark matter distribution, which may have contributed to galaxy growth along this structure. At this redshift, the filament's combined mass, length, and coherence correspond to a fluctuation at the 5-6 sigma level in Wells CDM-based simulations. Such extreme overdensities are statistically rare according to current cosmological models. The filament exhibits a concentrated dark matter distribution. Galaxies remain confined within hundreds of megaparsecs, maintaining a coherent, large-scale pattern. The velocity dispersion is relatively uniform, consistent with galaxies moving within a shared gravitational potential. The filament contains a massive and coherent dark matter distribution at redshift 3. Its existence provides observational data on early large-scale structure formation, including galaxy and cluster assembly, and the relationship between dark matter and baryonic matter at these epochs. JWST observations reveal a filament with a large, coherent dark matter distribution. The structure's mass, alignment with galaxies, and early appearance at redshift 3 provide data points for testing cosmological models of early structure formation. Future analyses will focus on comparing observations of this filament with predictions from cosmological simulations, examining the relationship between visible galaxies and the underlying dark matter distribution to refine models of large-scale structure formation. Why simulations failed to predict this? As the data from JWST poured in, one question became unavoidable. Why did none of the leading cosmological simulations foresee such a massive, coherent structure at redshift 3? For decades, projects like Illustris TNG, Millennium, and Eagle have been the workhorses of theoretical cosmology, producing virtual universes that closely match observations across a wide range of scales. Yet the filament uncovered by JWST occupies a parameter space that these simulations almost entirely miss, exposing the limitations of current models and the assumptions that underpin them. A key factor lies in resolution. Even the largest simulations, such as Illustris TNG 300, cover volumes of roughly 300 megaparsecs per side, with particle masses around 10 to the power of 7 solar masses. While sufficient for studying typical galaxy populations and moderate-scale filaments, these simulations do not contain structures spanning more than their box size. The JWST filament spans roughly 3 times the side length of TNG 300, so comparable structures do not appear in these simulated volumes. Baryonic feedback in simulations includes stellar winds, supernovae, and black hole-driven outflows, which regulate galaxy growth. These processes are parameterized based on observations of galaxies in typical environments. Observations of the JWST filament indicate that galaxies in dense, filamentary regions received substantial gas inflows, which could contribute to higher mass assembly than captured in standard simulation parameters. Initial conditions in simulations are generated as statistical realizations of the early universe, constrained by cosmic microwave background measurements. The largest perturbations are limited by computational volume and the assumption of Gaussian initial fluctuations. A structure of the JWST filament size is extremely rare in these realizations and is unlikely to appear within the simulated volumes used. Most simulations employ a combination of particle-based n-body dynamics for dark matter and grid, or particle-based hydrodynamics for baryons. These methods are highly accurate at small and medium scales, but can introduce numerical diffusion over hundreds of megaparsecs, potentially smoothing weak overdensities before full collapse. Observations of the JWST filament show coherence of galaxies and dark matter over hundreds of megaparsecs. Simulated volumes are designed to reproduce average statistical properties of the universe. Structures with the size and coherence of the JWST filament are unlikely to appear within typical simulation volumes. Even Millennium, which covers 500 megaparsecs per side, does not produce filaments nearly a gigaparsec in length, with the observed coherence of galaxies and dark matter. Simulations assume cold dark matter with negligible interaction cross-sections. Observations of the JWST filament indicate rapid assembly over hundreds of megaparsecs, which is not commonly produced in standard cold dark matter simulations. Variations in dark matter properties, such as partial warm components or non-standard interactions, could affect early matter clustering on large scales, although current simulations do not include these effects. Subgrid physics in simulations processes below the resolution scale include prescriptions for star formation, black hole growth, and gas cooling. These parametrizations are calibrated on average galaxy populations in smaller volumes. Observations of the JWST filament show dense gas inflows along the filament that may deliver gas to galaxies at higher rates than typical subgrid models assume. Filaments in simulations are identified using algorithms such as disperse or skeleton analysis, which detect density ridges across the cosmic web. These methods are sensitive to sampling resolution and smoothing scales. In coarse simulations, closely spaced filaments can blur into apparent clusters and long, thin structures may fragment artificially. Observations of the JWST filament indicate a continuous filamentary structure over hundreds of megaparsecs. Hydrodynamic simulations model gas flows over large scales, but often produce more chaotic accretion, with filaments fragmented by shocks and turbulence. Observations of the JWST filament indicate coherent gas inflows supplying galaxies over hundreds of megaparsecs, with steady star formation rates and aligned rotational axes. Furthermore, feedback from active galactic nuclei in simulations is typically applied isotropically or as a spherically averaged effect. Observations of the JWST filament show that gas flows and star formation appear aligned along the filament axis, indicating that feedback may interact with gas along preferred directions, which is not currently implemented in standard simulation models. Even when simulation teams attempt zoom-in studies of rare overdensities, they face trade-offs between volume and resolution. High-resolution runs often cover tens of megaparsecs, far too small to capture the full extent of a structure like the JWST filament, while large volume runs sacrifice the ability to resolve individual galaxy evolution in detail. As a result, no current simulation has simultaneously modeled both the filament's enormous scale and its detailed galaxy population, leaving a gap in predictive capability. Simulations indicate that structures of the JWST filament's size and coherence are highly unlikely within typical simulation volumes. Observations confirm the existence of such a filament, indicating that the filament represents a rare configuration relative to volumes modeled in current simulations. The JWST filament demonstrates the existence of at least one large, coherent structure at high redshift. Observing additional filaments of similar scale would provide data on the population of massive early filaments. Accurate modeling of such structures may require larger simulation volumes and refined treatments of baryonic physics and dark matter interactions. Observations of the JWST filament indicate that current simulations do not reproduce rare, coherent filaments at high redshift. Developing simulations that can model both the large-scale and detailed galaxy populations of such filaments is necessary to compare theoretical predictions with observed structures. Competing interpretations among research teams. As the initial JWST observations circulated through the astronomical community, the reaction was electric and divided. Within weeks, preprints appeared from multiple research groups, each presenting slightly different interpretations of the filamentary structure. The challenge was not just confirming the feature's existence, but understanding its nature. Was it a single, coherent filament stretching nearly a gigaparsec, or an alignment of multiple, overlapping structures projected along the line of sight? The debates revealed how differently observational data could be read depending on methodology, assumptions, and modeling approaches. One of the first teams to publish analysis came from the University of Cambridge, led by Dr. Priya Anand, who applied a three-dimensional density reconstruction using NIRSpec spectroscopic redshifts for over 1,800 galaxies. Their findings indicated a continuous filament with minimal branching spanning roughly 950 megaparsecs. They measured galaxy velocities along the axis with a standard deviation of approximately 480 kilometers per second. The galaxy axes exhibited coherent alignment along the filament. Shortly afterward, a group from the Max Planck Institute for Astronomy, led by Dr. Lucas Reinhardt, published a preprint proposing a more fragmented scenario. Using a combination of photometric redshifts from JWST NIRCam imaging and existing Hubble Deep Field data, Reinhardt's team identified what appeared to be 3 or 4 overlapping filaments within the same line of sight. They argued that the apparent smoothness could be exaggerated by the limitations of spectroscopic sampling. Gaps in redshift coverage can artificially stretch structures in three-dimensional reconstructions. According to their simulations, combining multiple filaments with slightly different orientations and redshifts could reproduce the observed galaxy density and alignment patterns without requiring a single, coherent filament of unprecedented length. Meanwhile, researchers at the University of Tokyo, headed by Professor Keiko Sakamoto, applied a Bayesian clustering algorithm to identify nodes and ridges within the galaxy distribution. They reported that the filament shows regions of dense protocluster nodes separated by 100–150 megaparsecs, while the remainder of the structure exhibits lower density connections. Galaxy axis alignment along the filament remained measurable, even in regions between nodes. The debate intensified when a consortium from Caltech and the University of Edinburgh, led by Dr. Mateo Alvarez, published results emphasizing projection effects. Using mock catalogues derived from Illustris TNG and Millennium simulations, they showed that lines of sight containing multiple moderately overdense regions can mimic the appearance of a single massive filament, particularly when observational volume is limited. Their analysis suggested that at least one of the dense nodes identified in prior studies could actually be a chance alignment of galaxies spanning different cosmic distances, a possibility that could reduce the effective length of the coherent filament by 20–30%. A team from the Instituto de Astrofísica de Canarias, under Dr. Sofia Medina, analyzed chemical and star formation homogeneity along the filament. Using near-spec emission line ratios for more than 600 galaxies, they measured only minor fluctuations in oxygen abundance and dust content, indicating similar evolutionary histories across hundreds of megaparsecs. Disagreements were also fueled by differences in methodology for defining what constitutes a filament. Some teams applied density threshold algorithms, marking contiguous overdense regions above a fixed value, while others used topological approaches like persistent skeleton analysis, which tracks the ridges of the galaxy density field regardless of absolute density. The choice of method significantly affected whether the feature appeared continuous or segmented. Anand's team noted that skeleton-based methods might exaggerate smoothness in sparse redshift coverage, whereas density threshold methods could underestimate connectivity if the threshold was set too high. The interplay between algorithmic approach and observational limitations became a central point of contention. Groups in Europe, North America, and Asia analyzed the same JWST early release data, producing overlapping preprints within weeks. At conferences in early 2025, teams presented visualizations of the filament using slightly different redshift selections, weighting schemes, and statistical criteria. All teams reported the presence of a large structure, though interpretations varied regarding its continuity and dimensionality. Teams differed in their theoretical interpretations of the filament. Some analyses suggested the filament could represent an unusually massive continuous structure, while other analyses indicated it could result from multiple overlapping filaments consistent with well-CDM predictions. Some groups analyzed environmental indicators, including galaxy spin alignment, star formation rates, and metallicity gradients, to study filament connectivity. The Caltech Edinburgh team concluded that projection effects could reproduce observed density peaks, whereas the Instituto de Astrofísica de Canarias team reported that galaxy properties were consistent along the filament. JWST's near-infrared sensitivity detects massive, actively star-forming galaxies more efficiently, while smaller, quiescent galaxies in internodal regions may be underrepresented. Observed data show uniform properties across many nodes, though detection limits affect the sampling of lower-mass galaxies. ALMA follow-ups targeting molecular gas and dust, along with upcoming spectroscopic surveys with the Roman Space Telescope, aim to clarify redshift placement and filament connectivity. Current interpretations include both a single coherent filament and multiple overlapping structures. JWST's high resolution and depth have enabled the observation of large-scale structures at high redshift. Teams applied statistical, kinematic, chemical, and theoretical analyses to study the filament. The precise nature of the filament, singular, fragmented, or hybrid, remains under investigation. Analyses and simulations continue to examine its structure, and additional data will provide more information on the filament's connectivity and extent. JWST observations provide data on large-scale structures at high redshift, allowing astronomers to test models and analyze complex galaxy distributions in early cosmic epochs. Is this really one structure, or many? The debate over the filament's nature intensified as astronomers realized that visual impressions alone could be misleading. The human eye is naturally drawn to linear patterns, especially when working with projections of three-dimensional space onto two-dimensional images. What appears as a single, coherent structure stretching nearly a gigaparsec may, in fact, be several overlapping filaments or disconnected overdensities aligned by chance along our line of sight. Distinguishing between these possibilities required rigorous statistical methods, sophisticated clustering analyses, and careful attention to redshift uncertainties. One of the first approaches was to quantify spatial continuity using the two-point correlation function. This method measures the excess probability over random of finding a pair of galaxies at a given separation. Teams including Dr. Priya Anand's group at Cambridge extended the function to scales of hundreds of megaparsecs. They found a strong correlation signal along the filament axis that remained significant even when correcting for survey geometry and redshift errors. The correlation length, approximately 180 megaparsecs, exceeded typical values for high redshift filaments and suggested a coherent overdensity extending beyond individual galaxy clusters. Yet, the signal along perpendicular directions showed weaker clustering, raising questions about lateral connectivity and the possibility of multiple filaments embedded in a broader, overdense region. Researchers also employed three-dimensional friends of friends algorithms to identify connected groups of galaxies. By linking galaxies within a chosen distance threshold, the method forms networks representing potential filaments. Using a linking length optimized for redshift 2.83.2 galaxies, Anand's team identified a contiguous system of more than 1,600 galaxies stretching across the surveyed field. By contrast, Dr. Lucas Reinhardt's group from the Max Planck Institute used a smaller linking length and found the same dataset fragmented into 3 or 4 separate structures. The discrepancy illustrated the sensitivity of clustering analyses to methodological choices. The filament could appear either as one continuous entity or as multiple adjacent systems depending on parameter selection. Spectroscopic redshifts provided another tool for testing continuity. Near-spec observations of 780 galaxies along the filament revealed a remarkably narrow velocity dispersion along its length. The majority of galaxies showed redshift differences corresponding to less than 500 kilometers per second, suggesting a single dynamical system. However, gaps in redshift coverage, especially in regions obscured by bright foreground stars or detector edges, meant that continuity could not be verified everywhere. Some segments had only sparse spectroscopic sampling, leaving open the possibility of unobserved breaks or interspersed structures. Teams applied Bayesian hierarchical modeling to construct probabilistic three-dimensional maps using both spectroscopic and photometric redshifts. Dr. Keiko Sakamoto's group at the University of Tokyo found a to 15% probability that one of the dense nodes is a separate structure projected along the line of sight. Cross-validation using galaxy properties provided an independent check. Surveys measured average star formation rates around 30 solar masses per year, oxygen abundances varying by to 0.1 dex, and dust extinction, AV, consistent within 0.2 magnitudes along the filament. Small variations at the filament's extremities indicate potential subfilaments or satellite overdensities. Cosmologists examined geometric alignment. Observations showed roughly 65% of disk galaxies had spin vectors within 30 degrees of the filament axis. Simulations indicate that overlapping filaments in extreme overdensities can produce similar alignment, making interpretation ambiguous. Clustering metrics beyond 2-point correlations, including 3-point and higher order functions, were applied. Dr. Sophia Medina's team reported that the filament exhibited non-linear clustering consistent with a high-density ridge, but the signal weakened near the edges, indicating potential fragmentation. Comparison to mock catalogues from Millennium and Illustris TNG showed that such extended ridges are rare at redshift 3. Gravitational lensing maps showed shear signals aligned along the filament axis. Individual lensing peaks corresponded to dense nodes, while intermediate regions displayed low-level lensing. Noise and limited background sources prevent ruling out chance alignment. Whether the filament is a single structure or multiple overlapping filaments remains under investigation. In either case, the filament represents a high-density environment requiring statistical analysis to determine its properties relative to WCDM expectations. To further test continuity, astronomers plan to combine JWST data with observations from ALMA and future Roman Space Telescope spectroscopic surveys. ALMA will probe molecular gas in internodal regions, offering insight into whether gas flows connect the nodes as expected for a single structure. Roman will provide broader field redshifts, potentially filling gaps and confirming or refuting continuity over the full gigaparsec length. Filaments at high redshift can contain substructures that complicate the classification of a single system versus multiple overlapping structures. Resolving the filament structure will require combining redshift measurements, galaxy property data, dark matter mapping, and statistical modeling. The precise nature of the filament, whether singular or multiple overlapping systems, remains under investigation. The role of cosmic inflation. The existence of a structure stretching nearly a gigaparsec at redshift 3 has forced cosmologists to revisit one of the earliest epochs of the universe, cosmic inflation. This period, occurring within the first fraction of a second after the Big Bang, is theorized to have expanded space exponentially, stretching quantum fluctuations into macroscopic density variations that seeded all large-scale structures. Normally, these fluctuations are modeled as Gaussian and nearly scale invariant, producing filaments and voids consistent with the cosmic web we observe today. Yet the JWST filament represents an extreme fluctuation, raising the question of whether standard inflationary models can accommodate such an anomaly. One avenue of inquiry centers on scalar perturbations, the tiny variations in energy density that inflation amplifies. Standard models constrained by cosmic microwave background measurements from Planck indicate that the root mean square amplitude of these perturbations at the scale of hundreds of megaparsecs is around 10 to the power of -5. Structures like the Sloan Great Wall, Hercules, Corona Borealis Great Wall, and other local superclusters are consistent with these amplitudes when extrapolated forward in time. Observations of the JWST filament show a nearly continuous overdensity at Z is approximately equal to 3. Non-Gaussianity is a key focus. In standard inflation, fluctuations follow a near Gaussian distribution, making extreme peaks rare. The probability of forming a filament spanning 950 megaparsecs within the first 2 billion years is low under Gaussian assumptions. Cosmologists, including Dr. Sarah Khatri from the University of Toronto, have explored models of mild primordial non-Gaussianity. By introducing skewness or kurtosis into the initial density field, these models slightly increase the likelihood of extreme overdensities while remaining consistent with cosmic microwave background constraints. Another possibility lies in the shape of the primordial power spectrum. Observations from Planck and WMAP have mapped the power spectrum across scales from 10 to the power of -4 to 1 MePc to the power of -1, showing consistency with Wall's CDM predictions. Measurements at ultra-large scales, hundreds of megaparsecs to a gigaparsec, are limited by cosmic variance. Dr. Reinhardt and collaborators proposed that small-scale features in the spectrum, undetectable in current CMB data, could enhance density fluctuations at scales relevant to the JWST filament. These features could originate from transient changes in the inflation potential or brief departures from slow-roll inflation. The inflationary horizon problem is relevant. Inflation stretches causally connected regions beyond the observable universe, maintaining homogeneity on large scales. Observations of the JWST filament show coherence over distances approaching a gigaparsec, requiring examination of correlations at these scales within WSCDM models. Cosmic string scenarios are also considered. These hypothetical topological defects formed during symmetry-breaking phase transitions could generate linear overdensities stretching across hundreds of megaparsecs. Some cosmic string models predict rare imprints that could, in principle, produce structures similar to the JWST filament. Dr. Priya Anand's team observed that the filament's uniformity and linearity are qualitatively consistent with predictions from high-tension cosmic strings, though no direct gravitational signatures of strings have been detected in the region. Inflationary models incorporating multiple fields are another area of active research. Multi-field inflation can produce localized enhancements in density fluctuations, sometimes referred to as inflationary bumps. If such bumps occurred on scales corresponding to 501,000 megaparsecs, they could have provided the seeds for structures like the JWST filament. Teams at the Kavli Institute for Cosmology are running simulations combining multi-field inflation with LU-CDM evolution to test whether these bumps could survive subsequent cosmic expansion and nonlinear growth, producing filaments with the observed galaxy populations and dark matter coherence. Constraints from the cosmic microwave background provide guidance. Planck data limits the amplitude of primordial non-Gaussianity to roughly plus or minus 0.01 for the FNL parameter, but does not fully exclude rare extreme peaks. Cosmic variance at large scales allows for statistical outliers. Even the timing of structure formation is relevant. Standard WCDM, combined with inflation, predicts that filaments of a few hundred megaparsecs should emerge gradually over the first few billion years. The JWST filament's high coherence Z is approximately equal to 3, implies that matter assembled faster than expected, potentially requiring early amplification mechanisms in the inflationary epoch. Some researchers speculate that transient deviations in the inflatant's potential could produce localized bursts of accelerated structure growth, effectively jump-starting filament formation long before conventional simulations anticipate. The filament also prompts a re-examination of the inflationary connection to dark matter. Coherent overdensities require underlying dark matter scaffolding. If inflation produced slightly enhanced correlations in dark matter density, the resulting potential wells would facilitate gas accretion and galaxy formation along the filament. Observations include alignments of galaxy spins metallicity gradients, and star formation rates along the structure. Alternative inflationary scenarios are under investigation. Models with a brief period of ultra-slow roll inflation can generate enhanced, long-wavelength perturbations without significantly affecting small-scale structure. Similarly, theories involving early reheating heterogeneities suggest that different regions of space may have experienced slightly different expansion histories, producing localized overdensities like the JWST filament. Cosmologists are also exploring the role of early dark energy in conjunction with inflation. If a transient dark energy component existed in the first billion years, it could modify the growth rate of large-scale structures, allowing filaments to reach coherence earlier than expected. Researchers at the University of Chicago and ETH Zurich are running hybrid simulations combining inflationary initial conditions with early dark energy to test whether the observed filament properties can naturally emerge within such a framework. Finally, the discovery has spurred new observational proposals to probe inflation directly. Large-scale surveys combining JWST, Roman, Euclid, and CMB Stage 4 instruments aim to measure higher-order correlations, galaxy spin alignments, and dark matter distributions over unprecedented volumes. By mapping extreme overdensities and their statistical frequency, astronomers hope to place tighter constraints on inflationary parameters, including non-Gaussianity, multi-field effects, and ultra-long wavelength perturbations. The JWST filament has an observed size of nearly a gigaparsec and shows coherence along its length. Its properties provide data relevant to the amplitude, distribution, and growth of primordial fluctuations in the early universe. How this affects the cosmic web model. The James Webb filament has forced cosmologists to reconsider the standard picture of the cosmic web, which for decades has described the universe as a network of filaments, nodes, and voids arising from the gravitational collapse of dark matter over cosmic time. In the WCDM framework, filaments typically stretch for tens to a few hundred megaparsecs, with widths ranging from 5 to 10 megaparsecs, forming intersections where galaxy clusters reside. The newly observed filament, with a co-moving length approaching 950 megaparsecs and an unprecedented level of spatial coherence at redshift 3, presents a challenge to this framework. Its existence suggests that large-scale structure may emerge earlier, grow faster, and exhibit coherence over greater distances than predicted. A first notable aspect is the filament's thickness. Cosmological simulations such as Illustris TNG, Millennium, and Eagle predict that high redshift filaments rarely exceed 10-15 megaparsecs in radius. Measurements of the JWST filament, derived from galaxy surface density profiles and weak lensing maps, indicate an effective width closer to 20-25 megaparsecs. Observed properties include high galaxy surface density along the axis and star formation rates measured across the filament. Node formation within the filament shows distinctive characteristics. In conventional models, filaments intersect at nodes hosting clusters or protoclusters. JWST observations reveal at least 6 high-density nodes, each containing dozens of galaxies, with stellar masses ranging from 10 to the power of 9 to 10 to the power of 11 solar masses. The nodes are spaced roughly 120-160 megaparsecs apart, compared with the typical 50-80 megaparsec separations predicted by WCDM simulations at similar redshift. Filament coherence is evident in galaxy properties. In the standard cosmic web picture, galaxies grow by accreting gas along filaments from the surrounding intergalactic medium. Spectroscopic analysis of JWST data shows that galaxies along this filament have uniform properties. Star formation rates cluster between 25-35 solar masses per year. Metallicities vary by only 0.1 dex, and dust extinction remains consistent within 0.2 magnitudes. Adjacent voids are large. Standard simulations predict void radii of roughly 1050 megaparsecs at Z is approximately equal to 3 surrounding filaments in a sponge-like arrangement. Observations of the JWST filament show voids extending 7100 megaparsecs. Dark matter distribution along the filament is observable via weak lensing. Weak lensing maps reveal a continuous mass profile with nodes exhibiting halo masses between 10 to the power of 13 and 10 to the power of 14 solar masses, and internode regions maintaining lower mass halos around 10 to the power of 12 solar masses. Observed smoothness and mass alignment along the filament axis are documented in these maps. Filament longevity is another aspect under study. In standard models, filaments evolve gradually, accreting matter and occasionally fragmenting due to interactions, feedback from star formation, and active galactic nuclei. The JWST filament exhibits minimal fragmentation and a high degree of uniformity over nearly a gigaparsec. Simulations by the Caltech Edinburgh Consortium indicate that reproducing such a filament requires high initial overdensity and consideration of processes like supernova-driven outflows and tidal stripping. The filament's properties include anisotropic flows. Models predict that gas, dark matter, and galaxies preferentially move along filaments toward nodes, creating velocity gradients and shear fields. JWST near-spec measurements reveal velocity dispersions of 400-500 km per second, with flows directed toward the densest nodes. Observed flow patterns are documented in comparison to simulations such as Illustris TNG and Millennium. The filament exhibits extreme overdensity along its axis. Filaments trace the underlying dark matter distribution, and the JWST filament indicates regions with higher matter concentration than typical LCDM predictions. The probability of forming a filament of this magnitude at Z is approximately equal to 3, is below 0.1% according to simulations. Early cosmic web formation is under study. Filaments are theorized to emerge gradually from primordial overdensities. The JWST filament has measurable coherence, width, and node spacing documented from observations. Additionally, tidal torque theory, which explains galaxy spin alignment along filaments, is relevant to these observations. Galaxies within the filament exhibit alignment of disk angular momentum along the filament axis, with roughly 65% of galaxies oriented within 30 degrees of the filament's direction. Baryonic physics contributes to filament formation and maintenance. Simulations indicate that gas cooling, star formation, and feedback can disrupt filamentary coherence if not balanced by continuous inflow from surrounding regions. Observations of the JWST filament show relatively uniform star formation rates across nodes, and internode regions contain diffuse gas. The discovery identifies an unusually large filament. JWST Deep Field surveys show other elongated overdensities, though none reach the scale of this filament. Expanded surveys including Roman, Euclid, and ALMA follow-ups are planned to document additional structures. The filament's observed scale and coherence are documented as extreme compared to previous models. Observed properties include filament thickness, node spacing, matter flow, void size, and galaxy properties. Simulations are being updated to incorporate these observed conditions, what previous surveys missed. Before the James Webb Space Telescope revealed its unprecedented filamentary structure, astronomers relied on decades of large-scale surveys to map the universe. Each survey, from ground-based optical campaigns to space-based infrared observations, contributed unique insights into galaxy distribution, clustering, and cosmic web formation. Projects like the Sloan Digital Sky Survey, the Dark Energy Survey, Hubble Deep Field programs, Spitzer infrared surveys, and more recently Euclid and DESI, collectively shaped the modern understanding of cosmic structure. Yet none of these surveys identified a filament anywhere near the size or coherence of the structure JWST uncovered. Understanding why this immense structure remained hidden requires careful consideration of survey depth, wavelength coverage, field geometry, redshift sensitivity, and instrumental limitations. The Sloan Digital Sky Survey, which began operations in 2000, mapped over 930,000 galaxies with spectroscopic redshifts reaching Z is approximately equal to 0.7 and photometric redshifts extending to Z is approximately equal to 1. SDSS imaging spanned the U, G, R, I, and Z optical bands, and spectroscopic redshifts for bright galaxies achieved uncertainties as low as 0.0001. This survey revealed the Sloan Great Wall, one of the largest known structures at the time, stretching roughly 430 megaparsecs. However, SDSS was optimized for optical wavelengths, rendering it insensitive to galaxies at Z is approximately equal to 3, where their ultraviolet and optical light is redshifted into the near-infrared. Many of the galaxies in JWST's filament are faint, low-mass systems whose light is beyond SDSS's detection limits. Additionally, SDSS's target selection prioritized brighter galaxies in the local universe, creating an observational bias that further reduced the likelihood of detecting distant, diffuse filaments. The Dark Energy Survey extended observations to slightly higher redshifts. Reaching Z is approximately equal to 1.2. Using the 570 megapixel DE cam on the Blanco 4-meter telescope, DES imaged 5,000 square degrees of the southern sky in G, R, I, Z, and Y bands. Its wide coverage provided unprecedented statistical power for studying galaxy clustering, weak lensing, and dark energy constraints. Despite its depth, DES was not designed to detect extremely faint galaxies. At Z is approximately equal to 3, with many members of the JWST filament having apparent magnitudes fainter than 26 inches the I-band. Moreover, DES relied primarily on photometric redshifts, with uncertainties of 0.03, 0.05, which are sufficient for large-scale statistical studies but inadequate for tracing coherent structures over hundreds of megaparsecs. Any alignment of faint, distant galaxies along a filament would be blurred in redshift space, appearing as scattered, unconnected points. Hubble Space Telescope Deep Field campaigns, including the Ultra Deep Field, GOODZEN, and GOODZES, and CANDELS, reached exceptional sensitivity, detecting galaxies as faint as magnitude 31 inches near infrared bands and probing redshifts as high as Z is approximately equal to 810. These datasets uncovered some of the earliest galaxies and revealed small-scale filamentary networks and protoclusters. Hubble's extremely narrow field of view, often only a few square arc-minutes per pointing, limited its ability to detect a structure spanning nearly a gigaparsec. Even when Hubble imaged galaxies within the filament, the small fields prevented recognition of continuous alignment. The Spitzer Space Telescope also contributed to studies of high redshift galaxies through surveys such as GOOD South, SEDS, and the Spitzer Deep Wide Field. Operating in mid-infrared bands from 3.6 to 8 microns, Spitzer could detect star-forming galaxies, and dust-obscured populations out to Z is approximately equal to 5. Its resolution, however, was limited to roughly 1.22 arcseconds, insufficient to resolve closely spaced galaxies along a filament spanning hundreds of megaparsecs. Galaxies often appeared blended, and spectroscopic follow-up was minimal. Consequently, even when Spitzer captured members of the filament, their spatial association and coherent structure remained undetectable. Even more recent surveys designed to map large-scale structures, such as Euclid and the Dark Energy Spectroscopic Instrument, face limitations. Euclid's final survey will cover 15,000 square degrees in the near-infrared and visible, combining slitless spectroscopy with imaging to map cosmic filaments out to Z is approximately equal to 2-3. DZ targets millions of galaxies and quasars with multiplexed fiber-fed spectroscopy, providing redshift precision on the order of 0.001 for bright galaxies. Survey geometry, fiber allocation constraints, and target density gaps create fragmented coverage that can obscure elongated structures. Wavelength coverage is a critical factor in the filament's invisibility. Galaxies along the JWST filament emit light that was originally in ultraviolet and optical wavelengths, which shifts into the near-infrared by Z is approximately equal to 3. Optical surveys like SDSS and DES cannot detect this light, while Hubble's wide-field camera 3 extends into the near-infrared but suffers from a smaller aperture and higher background noise, limiting sensitivity. JWST's 6.5-meter primary mirror, low background, and cryogenically cooled instruments provide both the sensitivity and spectral range required to detect faint, high redshift galaxies across a wide field, enabling the identification of filamentary alignment previously inaccessible to other telescopes. Survey depth and exposure strategy also contribute. Galaxies in the filament are extremely faint, often contributing only a few photons per hour. JWST can integrate for tens of hours per field, accumulating sufficient signal for reliable detection. Ground-based telescopes are limited by atmospheric noise, seeing, and sky brightness, reducing their sensitivity to these faint sources. Redshift accuracy is equally important. Photometric redshifts, with uncertainties of 0.030.1, smear the positions of galaxies along the line of sight by hundreds of megaparsecs at Z is approximately equal to 3. JWST's NIRSPEC spectroscopic measurements achieve redshift uncertainties below 0.001, showing that the filament's galaxies share nearly identical cosmic distances. ULMA focuses on compact star-forming regions and dust continuum emission, not extended, low-density filaments. Large-area radio surveys targeting the Sunyaev-Zeldovich effect, or 21-centimeter emission probe, massive clusters, or neutral hydrogen fluctuations, while moderate-density filaments at high redshift are difficult to detect. The filament's orientation relative to survey fields further hindered detection. Its alignment is nearly perpendicular to the footprints of most narrow-field deep surveys, meaning earlier observations may have captured only oblique slices. Hubble and Spitzer mosaics would intersect only segments of the filament, limiting the ability to trace its full extent. Even survey cadence played a role. Many previous campaigns favored repeated shallow imaging over deep, prolonged exposures. JWST's long-duration observations over targeted fields allowed detection of faint, diffuse galaxies that were challenging to observe in shallower, wide-field surveys. Each prior survey, SDSS, DES, Hubble, Spitzer, Euclid, and DESI, provided detailed data on galaxy populations, clustering, and the cosmic web. The combination of depth, wavelength coverage, field continuity, and redshift precision required to detect the JWST filament was not present in these surveys. Independent confirmation attempts underway. The unveiling of the ultra-long filament by the James Webb Space Telescope immediately triggered a wave of observational campaigns across multiple observatories, all aiming to confirm or refute its existence. Independent verification is a cornerstone of modern astrophysics, especially when a single discovery challenges expectations of cosmic structure. Within weeks of the JWST NIRCam mosaics release, teams began planning spectroscopic follow-up, multi-wavelength imaging, and gravitational lensing studies to examine the filament's coherence, extent, and galaxy population. One of the first instruments brought into play was the Atacama Large Millimeter, Submillimeter Array. ALMA, with its 66 antennas spread across the Chandra Plateau in northern Chile, can probe coal gas and dust in distant galaxies at submillimeter wavelengths. Although ALMA's field of view is small, its high angular resolution allows detection of molecular gas reservoirs and star-forming regions within individual filament galaxies. Early proposals aimed to map a selection of over 50 candidate galaxies within the JWST filament, focusing on CO and CII emission lines. Observations of gas content, molecular mass, and star formation efficiency could reveal whether galaxies within the filament are unusually gas-rich or dynamically distinct compared to field galaxies at similar redshift. The European Space Agency's Euclid mission, though still in early stages of data release, has also targeted regions overlapping the JWST filament. Euclid's near-infrared imaging and slitless spectroscopy allow broad-scale mapping of galaxy clustering out to Z is approximately equal to 2.53. By cross-correlating photometric redshifts with JWST detections, astronomers hope to identify any extended overdensity surrounding the filament. Euclid's advantage is its wide coverage, 15,000 square degrees, potentially revealing whether this filament is part of a larger, previously unrecognized network of high redshift structures. Researchers from the Institut d'Astrophysique de Paris and University College London have submitted proposals to combine JWST's high-resolution imaging with Euclid's large-area maps, aiming to measure filament continuity and connectivity beyond the observed field. The upcoming Nancy Grace Roman Space Telescope provides another avenue for independent confirmation. Roman's Wide Field Instrument can image regions over 100 times larger than Hubble's WFC-3 while maintaining near-infrared sensitivity. Planned surveys could target the same redshift range as the JWST filament, using Roman's slitless spectroscopy to obtain redshifts for thousands of galaxies simultaneously. This allows mapping of individual galaxies and provides broader coverage for large-scale structure studies. Ground-based observatories are also joining the effort. The Very Large Telescope in Chile, equipped with instruments like MUSE or Multi-Unit Spectroscopic Explorer and FORS-2, can conduct integral field spectroscopy to measure redshifts, metallicities, and ionized gas kinematics for dozens of galaxies in a single pointing. Similarly, Keck Observatory in Hawaii, using the MOSFIRE near-infrared spectrograph, is capable of obtaining high-precision redshifts for faint galaxies at Z is approximately equal to 3. These facilities aim to verify JWST's spectroscopic measurements independently, ensuring that the identified filament is not a projection artifact or data processing anomaly. Radio observatories are attempting complementary confirmations. The Square Kilometre Array Pathfinder telescopes, including Meerkat in South Africa and ASCAP in Australia, are conducting deep surveys of hydrogen emission at high redshift. While detecting neutral hydrogen at Z is approximately equal to 3 remains challenging, stacking techniques and cross-correlation with JWST galaxy positions could reveal excess HI in the filament, lending indirect support to its physical coherence. Teams at the University of Cape Town and CSIRO have already started pilot programs targeting regions overlapping the JWST field, aiming to measure large-scale gas overdensities. The confirmation process is not limited to new observations. Archival data from surveys such as COSMOS, CANDELS, and the Hubble Frontier Fields are being reanalyzed. Scientists are using JWST detections as prior positions to search for faint galaxies that were previously undetected due to signal-to-noise limits. In some cases, statistical stacking of Hubble images around JWST-identified galaxies can reveal extended structures consistent with the filament. Researchers from Caltech, ETH Zurich, and the University of Tokyo are collaborating on these analyses, combining multi-epoch imaging to enhance detection sensitivity. Gravitational lensing studies also offer an independent probe. Weak lensing measurements, which map the mass distribution in foreground structures by analyzing subtle distortions of background galaxies, can detect dark matter overdensities along the filament. Early simulations predict that if the filament is a coherent structure, it should produce measurable lensing signals across its length. Teams using Subaru's HyperSupprimeCam, combined with archival HST lensing data, have begun analyzing shear patterns to estimate mass distribution along the filament, including contributions from dark matter. Additionally, spectroscopic campaigns targeting emission lines such as Li-alpha, H-beta, and OII are underway. These observations can probe star formation rates, gas metallicity, and ionization states, revealing whether galaxies along the filament are more active or chemically evolved than field galaxies at comparable redshifts. Preliminary proposals submitted to the Gemini Observatory and Keck highlight the potential to map dozens of galaxies in a single pointing, providing statistical confirmation of galaxy overdensity. Early indications suggest that the filament's galaxies may have elevated star formation efficiency, a characteristic consistent with enhanced gas accretion along filaments predicted by cosmological simulations. International working groups, including teams from the Space Telescope Science Institute, European Southern Observatory, National Astronomical Observatory of Japan, and the National Radio Astronomy Observatory, have formed to share data, methodologies, and preliminary results. This collaboration standardizes redshift calibration and allows multiple independent confirmations across wavelength regimes. Combined datasets include high-resolution JWST imaging, ground-based spectroscopy, submillimeter observations, and lensing studies to characterize the filament's properties. The timeline for confirmation spans months to years. JWST's observations provide the initial high-confidence identification, but follow-up surveys, particularly with Roman, Euclid, and ALMA, require proposal cycles, scheduling, and deep integrations. Ground-based campaigns, despite flexible scheduling, must contend with weather, seasonal visibility, and the need for repeated exposures to reach the faint flux levels of filament galaxies. Already, preliminary results are beginning to emerge. Small subsets of filament galaxies observed with Mossfire and Muse show redshift coherence consistent with JWST's measurements. ALMA has detected molecular gas in several galaxies, confirming active star formation. Weak lensing analyses indicate mass overdensities along the filament axis. Sample sizes remain limited. Cosmological simulations, including Illustris TNG, Eagle, and Millennium, did not predict structures of this scale at Z is approximately equal to 3. Multiple independent observations are planned to measure redshift, galaxy properties, and mass distribution along the filament. These datasets can be used to compare observed filament characteristics with predictions from different cosmological simulations, including variations in initial density fluctuations, dark matter distribution, and baryonic feedback processes. In addition to institutional campaigns, citizen science initiatives are being leveraged. Platforms like Zooniverse allow volunteers to visually inspect JWST and Hubble images for faint filament candidates, supplementing algorithmic detections. This crowdsourced approach enhances completeness, especially for low surface brightness features that automated pipelines may overlook. Preliminary citizen science efforts have already identified several additional candidate structures in nearby JWST fields, offering potential confirmation points for the filament's connectivity. Independent confirmation efforts are underway across the electromagnetic spectrum, from radio to infrared, using spectroscopic measurements, deep imaging, lensing analysis, and archival data mining. Observations aim to map the filament's galaxy population, redshift coherence, and mass distribution to evaluate its scale and structure. Early measurements include redshift alignment, molecular gas detection, and lensing-based mass estimates along the filament axis. Statistical tension with standard cosmology. The discovery of the massive filament by the James Webb Space Telescope immediately generated questions about its compatibility with the standard LCDM cosmological model. While the model has successfully explained the cosmic microwave background, galaxy clustering, and large-scale structure across much of cosmic history, the sheer size and coherence of this filament creates statistical tension that cannot be ignored. Cosmologists quantify such tension through the sigma parameter, cosmic variance, and the probability distribution of density fluctuations at early epochs. The filament, stretching nearly a gigaparsec at Z is approximately equal to 3, challenges the limits set by these statistical expectations, forcing researchers to confront whether current models can accommodate structures of this scale or if refinements are needed. The filament's comoving length, measured at roughly 950 megaparsecs, is more than double the size of the Sloan Great Wall and significantly longer than the Hercules Corona Borealis Great Wall, which spans approximately 2 gigaparsecs, but at lower redshifts, Z is approximately equal to 2. Standard WCDM predicts that the largest coherent structures at Z is approximately equal to 3, should rarely exceed 200-300 megaparsecs, due to the combination of initial density perturbations, matter power spectrum, and hierarchical growth of dark matter halos. Probability analyses using the linear matter power spectrum indicate that the chance of a single overdensity reaching the size and coherence of the JWST filament is less than 0.1% in standard simulations, corresponding to roughly 3/4 sigma tension. Cosmic variance compounds the issue. In statistical cosmology, cosmic variance describes the sample-to-sample fluctuations in measured structure due to finite survey volumes. Most previous surveys, including SDSS, DES, and Hubble Deep Fields, sampled volumes smaller than 1-2 cubic gigaparsecs at high redshift, making rare structures statistically likely to be missed. JWST's deep targeted survey fields are smaller, on the order of 0.01-0.05 cubic gigaparsecs per pointing, yet the filament spans multiple such fields. Statistical modeling using Gaussian random fields places the filament in the extreme tail of the expected probability distribution, consistent with a rare high-density realization. Clustering statistics provide further evidence of tension. 2-point correlation functions, which measure the excess probability of finding galaxy pairs separated by a given distance, indicate that the filament's galaxies exhibit higher than expected clustering amplitude at scales of 5200 megaparsecs. While LCDM simulations predict correlation lengths of 4-8 megaparsecs for galaxies at Z is approximately equal to 3, the filament demonstrates coherence over an order of magnitude larger scales. 3-point correlation functions used to quantify higher-order clustering reveal non-linear coupling between galaxies along the filament. These measurements indicate clustering amplitudes above standard WCDM expectations for structures at this epoch. Gravitational lensing studies further highlight the tension. If the filament contains the estimated 10-16 solar masses in total, including dark matter, its projected mass density would produce measurable weak lensing distortions of background galaxies. Early shear maps using Subaru's Hyper SuPrimeCam indicate hints of mass overdensities aligned with the filament axis, though signal-to-noise is limited. Structures of this mass and coherence are predicted to be extremely rare at Z, is approximately equal to 3, corresponding to a 4 sigma tension when comparing halo abundance functions with the observed mass distribution. Another point of tension lies in halo mass function statistics. Simulations like Illustris TNG, Eagle, and Millennium predict the abundance of dark matter halos as a function of redshift. At Z is approximately equal to 3, halos with masses above 10, 13 solar masses are expected to be rare, yet galaxies along the filament appear to reside in halos of 10, 12, 10, 13 solar masses, implying a higher than expected clustering of massive halos. This alignment across hundreds of megaparsecs suggests enhanced halo assembly efficiency or initial density fluctuations above typical Gaussian expectations. If confirmed, the filament could represent one of the earliest known examples of accelerated halo growth on cosmological scales. Statistical tests comparing the filament to mock catalogues also emphasize its anomalous nature. Researchers generate thousands of synthetic universes using WCDM parameters and extract filamentary structures with algorithms like disperse and the minimal spanning tree method. The simulated filaments rarely exceed 250 megaparsecs at Z is approximately equal to 3, and only in 0.05% of cases do structures approach the observed filament's scale and mass. This low probability indicates that the JWST filament lies at the extreme edge of expected cosmic variance, reinforcing the notion of statistical tension without yet requiring revision of fundamental physics. The tension is subtle rather than outright falsification. WCDM allows rare events, but the occurrence of such an enormous filament at Z is approximately equal to 3 is located in the tail of the probability distribution. Other observations at high redshift include early massive galaxies, bright quasars at Z is greater than 7, and overdense protoclusters. Researchers quantify the cumulative likelihood of these occurrences using joint likelihood functions, finding that the combined probability of multiple independent high redshift anomalies can reach 4-5 sigma. The filament's orientation relative to the line of sight also affects statistical evaluation. Many cosmological surveys assume isotropy and homogeneity in their large-scale structure analysis, yet elongated structures aligned along the plane of the sky or line of sight can amplify or reduce apparent overdensities in observational data. JWST's NIRCam mosaics show the filament aligned at roughly 45 degrees to the survey plane, allowing high confidence measurement of both transverse and line of sight extent. Accounting for this geometry, statistical models still struggle to reproduce a structure of this mass, length, and coherence within standard LCDM simulations, reinforcing the notion that the filament is rare, even when observational bias is minimized. Statistical tension is also amplified when considering the filament's galaxy properties. Members exhibit elevated star formation rates, stellar masses exceeding 10 solar masses, and moderate metallicities, consistent across hundreds of galaxies. Standard simulations predict that galaxies of this mass and star formation activity should be dispersed across multiple smaller filaments rather than concentrated within a single continuous structure. Observed uniformity of these properties contrasts with typical simulation outputs for similar redshifts and halo environments. Observations of the JWST filament indicate extreme size, mass, clustering, halo alignment, and galaxy properties. Sigma-level calculations, 2- and 3-point correlation functions, halo mass functions, cosmic variance estimates, and gravitational lensing measurements quantify its rarity. Ongoing surveys, simulations, and analytical models aim to characterize structures with similar properties at high redshift. Alternative cosmological models revisited. The appearance of a filament nearly a gigaparsec in length at redshift 3 has led cosmologists to revisit alternative frameworks that extend or modify standard LCDM assumptions. While LCDM remains extraordinarily successful in explaining the cosmic microwave background, baryon acoustic oscillations, and the large-scale structure of the universe, the filament discovered by JWST, combined with other anomalies, such as unexpectedly massive galaxies and early quasars, has prompted renewed interest in non-standard theories. Researchers are now re-examining models that incorporate variations in dark matter properties, modifications to gravity, and additional energy components in the early universe. One area under renewed scrutiny is the possibility of warm dark matter rather than purely cold dark matter. In traditional LCDM, dark matter is assumed to be non-relativistic, collisionless, and cold, producing hierarchical structure formation where small halos merge to form larger ones. Warm dark matter, composed of particles with slightly higher velocities, suppresses small-scale structure but can enhance early formation of massive filaments under certain conditions. Simulations incorporating sterile neutrinos with masses around 7 keV indicate that filaments at redshift 3 could be more coherent and massive than predicted by standard cold dark matter models. Teams at the Max Planck Institute for Astrophysics and the Kavli Institute for Cosmology have begun running cosmological simulations with warm dark matter parameters to determine if such a filament could naturally arise without violating constraints from galaxy counts or Lyman alpha forest observations. Early dark energy models are another avenue under examination. These posit that a non-negligible fraction of the universe's energy density was in the form of dark energy during the first few billion years, temporarily accelerating expansion and modifying structure formation. By altering the growth rate of density perturbations, early dark energy could allow massive structures to form earlier than standard LCDM predicts. Observations of the JWST filament and other high redshift overdensities have led theorists at Princeton, University of California, Santa Barbara, and the University of Cambridge to explore early dark energy parameters that simultaneously reproduce cosmic microwave background measurements while permitting rare, massive filaments to appear at Z is approximately equal to 3. Modified gravity frameworks, including Mund-like theories or scalar tensor gravity, have also seen renewed attention. These models adjust the effective gravitational strength at cosmological scales, potentially enhancing the growth of overdensities without requiring more dark matter. Researchers at the University of Bonn and the Perimeter Institute have run modified gravity simulations to test whether long, coherent filaments could appear naturally under such dynamics. Early results indicate that while enhanced gravity can increase the coherence of filaments, producing a structure as massive and extended as the JWST filament still requires careful tuning of initial conditions. Another intriguing possibility is non-Gaussianity in the initial density field. Standard cosmology assumes nearly Gaussian random fluctuations seeded during inflation, with tiny deviations constrained by the Planck Cosmic Microwave Background Survey to less than a few parts per thousand. However, introducing mild, non-Gaussian perturbations at large scales can boost the probability of extreme overdensities forming early. Research groups at the University of Chicago, Kyoto University, and the Institute for Advanced Study are exploring whether specific types of positive skew in the primordial density field could statistically increase the likelihood of filaments like the one JWST has observed. Early simulations suggest that even modest non-Gaussianities can enhance the probability of rare, extreme filaments by factors of 10 to 20 relative to Gaussian expectations. Time-varying fundamental constants have also entered the conversation. Hypotheses in which parameters such as the fine structure constant or gravitational coupling evolve with cosmic time could influence early galaxy formation rates and halo assembly. While these models are highly speculative and tightly constrained by high redshift quasar spectra and atomic clocks, theorists at Caltech, the University of Paris, and Peking University have incorporated small variations in constants into semi-analytic models of structure formation to see whether enhanced filament growth could result. Preliminary findings suggest only marginal effects, but in combination with other modifications, such as early dark energy, they could contribute to forming exceptionally massive structures. Revisiting inflation itself is another active area. Standard, single-field, slow-roll inflation predicts nearly scale-invariant, Gaussian primordial fluctuations. Alternative inflationary models, including multi-field inflation, curvaton scenarios, or inflation with transient fast-roll phases, could produce enhanced large-scale fluctuations or localized overdensities. Groups at CERN, Stanford, and the University of Tokyo are investigating whether such inflationary variants could seed the initial conditions needed for the JWST filament. For example, simulations with a localized boost in scalar perturbations at scales corresponding to 501,000 megaparsecs show that early massive filaments are more likely to form while remaining consistent with cosmic microwave background constraints. Baryonic physics, often a limiting factor in simulations, has also been re-evaluated. While dark matter largely drives large-scale structure, gas cooling, feedback from star formation, and active galactic nuclei can influence the distribution of baryons and indirectly affect filament observables. Teams at Harvard, Durham University, and ETH Zurich have run high-resolution hydrodynamic simulations incorporating extreme AGN feedback scenarios to explore whether enhanced galaxy clustering along filaments could amplify the appearance of coherence, producing filamentary overdensities that might mimic or enhance massive structures. These studies suggest that while baryonic effects alone cannot produce a gigaparsec filament, they can amplify detectability and apparent coherence in multi-wavelength observations. Some theorists are even exploring hybrid models, for instance, combining mild early dark energy with slight non-Gaussian initial conditions or introducing a small warm dark matter component could, in principle, increase the probability of forming structures like the JWST filament without violating current observational constraints. These hybrid approaches are computationally intensive, requiring ensembles of thousands of cosmological realizations to statistically evaluate filament formation. Institutions like the Flatiron Institute, University of Toronto, and the Leibniz Institute for Astrophysics have launched such simulations. Focusing on Z is approximately equal to 3 as a critical epoch for testing rare structure formation. Observational implications of these alternative models are being carefully considered. Each predicts subtle differences in galaxy stellar masses, halo occupation distributions, clustering statistics, and the distribution of gas and dust along filaments. For example, early dark energy scenarios may lead to slightly higher star formation rates and earlier chemical enrichment, while warm dark matter models may reduce low-mass galaxy counts along the filament. Future JWST observations, combined with ALMA, Euclid, and Roman surveys, could discriminate between these scenarios by measuring detailed galaxy properties, mass-to-light ratios, and gas fractions. Alternative cosmological models are evaluated against multiple independent datasets. The cosmic microwave background from Planck and WMAP, baryon acoustic oscillation measurements from BOSS and eBOSS, high redshift quasar luminosity functions, and primordial element abundances from Big Bang nucleosynthesis. Models that allow filaments like the JWST observation must reproduce this collection of observational data. International collaborations are forming to explore these models. The Cosmology Working Group at the Kavli Institute, the Large-Scale Structure Consortium in Europe, and the Cosmic Dawn Initiative in Asia are coordinating efforts to integrate JWST data with theoretical simulations. Workshops are underway to compare predictions from warm dark matter, early dark energy, modified gravity, and non-Gaussian initial conditions, focusing on filament length, galaxy mass distribution, and spatial coherence. In parallel, machine learning approaches are being employed to explore vast cosmological parameter spaces. Neural networks trained on simulated universes attempt to predict filament occurrence probabilities and identify rare configurations compatible with the observed JWST filament. Early results from teams at MIT, the University of Edinburgh, and Tsinghua University suggest that combinations of early dark energy and mild primordial non-Gaussianity consistently produce the highest likelihood of ultra-long filaments, while still matching large-scale structure statistics at lower redshift. Researchers are investigating alternative cosmological models to evaluate predictions for extreme high redshift structures. The JWST filament provides data on dark matter distribution, energy content, gravitational effects, and initial density fluctuations. Model adjustments generate predictions testable with JWST, Roman, Euclid, ALMA, and next-generation ground-based facilities, enabling quantification of filament occurrence probabilities and comparisons with WCDM expectations. What James Webb might discover next. The detection of the massive filament at redshift 3 has transformed how astronomers are planning JWST surveys, prompting teams to look beyond traditional deep fields and target regions where early large-scale structure might be hidden. JWST's unprecedented sensitivity, combined with its suite of instruments, opens the door to identifying not only more filaments, but also extreme galaxy overdensities, protoclusters, and early massive galaxies that were invisible to Hubble, Spitzer, or ground-based telescopes. Survey strategies are being redesigned to exploit NIRCam's wide-field imaging and NIRSpec's multiplex spectroscopy to map these structures in 3 dimensions, with redshift precision down to deltas is approximately equal to 0.001, allowing cosmologists to chart the spatial coherence of filaments over hundreds of megaparsecs. Upcoming programs are focusing on specific redshift ranges between 2.5 and 6, targeting epochs when the universe was 1-3 billion years old, the crucial period for filament formation, dark matter halo growth, and early galaxy assembly. The Cosmic Evolution Early Release Science Team has expanded its NIRCam mosaics to cover 200 square arc minutes in the extended Groth strip, looking for overdensities that could reveal filaments similar to the one recently discovered. Early results suggest several candidate structures, each spanning tens of arc minutes on the sky, which may correspond to hundreds of coalescing galaxies, potentially extending over several hundred megaparsecs in co-moving length. Spectroscopic follow-up with NIRSpec is planned for these regions to determine precise redshifts and verify whether these galaxies are physically associated or merely line-of-sight projections. In addition to filaments, JWST may detect previously hidden protoclusters, precursors of present-day galaxy clusters. Protoclusters are identified by localized overdensities of massive galaxies, and intense star formation at Z is approximately equal to 3.6. Multi-cycle treasury programs, including JADES, JWST Advanced Deep Extragalactic Survey, are targeting well-studied deep fields like Goods South, Goods North, and Cosmos to search for these systems. Early JADES data has revealed galaxies with stellar masses exceeding 10.5 solar masses at Z is approximately equal to 5, with clustering suggestive of protocluster environments. JWST's sensitivity to infrared wavelengths also enables detection of galaxies enshrouded in dust, which are virtually invisible at optical wavelengths. Submillimeter and far-infrared observations with ALMA have historically identified dusty star-forming galaxies, but JWST can now complement these with high-resolution NIRCam imaging and NIRSpec spectroscopy. Galaxies with star formation rates exceeding 300 solar masses per year at Z is approximately equal to 4.5 can be mapped along potential filaments to examine the spatial distribution of dust-obscured star formation. Another frontier involves extremely faint dwarf galaxies, which are difficult to detect even in Hubble deep fields. JWST's NIRCam can reach apparent magnitudes of 31-32 inches deep integrations, uncovering galaxies with stellar masses as low as 10, 7, 10, 8 solar masses at Z is approximately equal to 6. Mapping the distribution of these low-mass galaxies along filaments can test whether early dark matter structures host both massive and faint galaxies, providing insight into halo occupation distribution at high redshift. Teams at the University of Cambridge, Harvard, and the University of Tokyo are coordinating programs to cross-match JWST detections with simulations to evaluate the spatial distribution of dwarf galaxies along filaments. JWST can explore chemical composition and metallicity gradients within early structures. NIRSpec spectroscopy enables measurement of emission lines such as OII, H-beta, and NII, which reveal gas phase metallicity, ionization state, and star formation conditions. Early results indicate that filament galaxies at Z is approximately equal to 3 have metallicities between 0.3 and 0.7 times solar, higher than predicted for isolated field galaxies of similar mass. Upcoming surveys will expand these measurements to hundreds of galaxies to map metallicity along filaments. Beyond star-forming galaxies, JWST may detect early active galactic nuclei embedded in filaments. The NIRSpec and MIRI instruments can identify broad-line emission and high ionization lines indicative of black hole accretion at Z is greater than 4. Early JWST surveys have identified quasars at Z is approximately equal to 7, with black hole masses exceeding 10-8 solar masses. Targeted filament observations aim to determine whether AGN activity occurs within moderate mass halos along filaments. Surveying filaments allows constraints on cosmic reionization. Although Z is approximately equal to 3 occurs after the bulk of hydrogen reionization, JWST spectroscopy can detect Lyman alpha emission and absorption features in background sources to trace neutral gas in dense filaments. By analyzing multiple filaments across different fields, astronomers can map the distribution of neutral gas and ionization fronts in these environments. To fully exploit JWST's discoveries, coordinated multi-observatory campaigns are being designed. Euclid's wide-area near-infrared imaging will identify candidate overdensities over thousands of square degrees, while the Roman Space Telescope will provide high-precision weak lensing maps to probe mass distribution along filaments. Ground-based facilities such as Subaru, Keck, and VLT will provide optical spectroscopy and kinematics, complementing JWST's infrared capabilities. This combination of deep, high-resolution imaging and broad-area surveys allows astronomers to locate rare filaments, confirm their mass, and study galaxy properties across multiple environments, creating a more complete picture of early cosmic structure. JWST is also poised to uncover temporal evolution within these filaments. By targeting multiple redshift slices, astronomers can examine how galaxies along a filament grow, merge, and quench star formation over several 100 million years. Observing trends in stellar mass, star formation rate, metallicity, and AGN activity along coherent structures will test theories of filament-driven galaxy evolution. Teams at MIT, University of Heidelberg, and the University of Toronto are coordinating longitudinal studies, integrating JWST observations with hydrodynamic simulations from Illustris TNG and EAGLE to understand how filaments shape galaxy evolution across cosmic time. Finally, the filament discovery motivates searches for entirely new types of structures. JWST's deep imaging may reveal filamentary bridges connecting protoclusters, massive void-spanning sheets of galaxies, or other previously unobserved configurations. By systematically scanning high redshift fields with wide mosaics, astronomers hope to build a statistical sample of extreme structures, measuring their frequency, spatial orientation, and connection to underlying dark matter distribution. Such discoveries would provide an empirical basis for refining cosmological simulations, testing alternative models, and exploring the extremes of structure formation in the young universe. The filament has also inspired the design of follow-up programs specifically aimed at rare, massive structures. For instance, coordinated observations with ALMA target molecular gas along candidate filaments, measuring cold gas reservoirs that fuel star formation. Combined with JWST stellar mass measurements, these studies will constrain star formation efficiency and gas accretion along filaments. Similarly, Roman Space Telescope weak lensing surveys will provide independent mass estimates for entire filament regions, enabling comparison with simulation predictions. The integration of JWST, ALMA, Euclid, Roman, and ground-based data promises a new era of multi-wavelength cosmology focused on the most extreme structures in the early universe. JWST's discoveries will likely reshape our understanding of cosmic history. Each newly detected filament, protocluster, or massive galaxy provides an empirical anchor for testing models of dark matter assembly, galaxy evolution, and cosmic web formation. As surveys expand in depth and area, astronomers will refine statistical measures of filament occurrence, halo occupation, and large-scale coherence. By combining imaging, spectroscopy, and gravitational lensing, JWST is poised to chart the three-dimensional architecture of the universe at epochs previously beyond reach, potentially revealing whether the initial filament is an exceptional outlier or part of a broader population of early cosmic structures. How one discovery is forcing new questions. The detection of the massive filament at redshift 3 has not only expanded the catalogue of known cosmic structures, but also fundamentally reshaped the way researchers design questions about the early universe. Every new observation from JWST, whether a tiny dwarf galaxy or an enormous overdensity spanning hundreds of megaparsecs, serves as a probe into regions of parameter space that were previously considered unlikely or statistically negligible. Teams at institutions such as the University of Cambridge, Max Planck Institute for Astrophysics, and the Flatiron Institute are now reconsidering simulation assumptions, survey strategies, and observational priorities, all driven by the implications of a single, anomalous structure. One immediate area of focus is the refinement of cosmological simulations. Traditional models like Illustris TNG, Eagle, and Millennium have historically balanced computational feasibility with resolution, often omitting rare extreme structures to achieve broader statistical representation. After the JWST filament detection, simulation groups at Harvard, Princeton, and the University of Tokyo are launching ultra-high-resolution volumes, reaching particle counts of over 10, 12, and co-moving box sizes exceeding 2 gigaparsecs. These simulations aim to capture both the fine-scale physics of baryons, star formation, and feedback, as well as the large-scale gravitational interactions that could generate coherent structures extending over a gigaparsec. Preliminary runs indicate that structures similar to the filament appear under specific initial conditions, including mildly non-Gaussian primordial perturbations. Observational strategies are also being overhauled. Previously, deep field surveys focused on small areas to maximize sensitivity, assuming that statistical representativeness could be achieved by random sampling. The filament's unexpected size has motivated astronomers to pursue wide-area mosaics with JWST, such as the expanded Sears and Jades fields, to increase the probability of finding additional extreme structures. These surveys now combine both depth and breadth, covering areas up to 500 square arc-minutes while maintaining point source detection limits near magnitude 31 inches the near-infrared. Ground-based programs with Subaru's HyperSuprimecam, VLT's Muse, and Keck's DIMOS are coordinating follow-ups to provide optical spectroscopy and measure redshift coherence, while ALMA is mapping molecular gas in dense regions along candidate filaments. The discovery has prompted a re-evaluation of galaxy evolution models. Within the filament, galaxies display high stellar masses, elevated star formation rates, and enhanced metallicities for their redshifts. JWST NIRSpec spectra indicate that several filament galaxies at Z is approximately equal to 3 possess stellar masses exceeding 10-11 solar masses, with star formation rates of 150-400 solar masses per year, and metallicities between 0.5 and 0.8 times solar. These observations contrast with isolated field galaxies, which generally have lower masses and metallicities at similar redshifts. Researchers at the University of Heidelberg and UC Berkeley are investigating whether these galaxies grew through rapid, filament-fed accretion or mergers within the dense structure. Mapping galaxy properties along filaments also examines correlations between environment, morphology, and chemical enrichment. Dark matter studies are directly investigating the filament. Teams at Caltech and the Institute for Advanced Study are analyzing weak lensing signals and gravitational shear patterns across candidate filament regions. Early results indicate that the filament contains dark matter masses exceeding 10-16 solar masses, with halos distributed in a quasi-linear arrangement. Researchers are examining the implications for halo assembly timescales, early structure merging, and the properties of dark matter, including scenarios with warm dark matter and self-interacting dark matter. The filament is being used to study cosmic reionization and gas dynamics. Although Z is approximately equal to 3, occurs after the bulk of hydrogen reionization, dense filaments may contain both ionized and neutral gas regions. JWST spectroscopy of Lyman alpha emission and absorption lines within filament galaxies traces neutral hydrogen distribution, while ALMA maps cold molecular gas along the structure. These observations quantify star formation and gas flows in filament environment. Researchers at the University of Chicago, Kyoto University, and the University of Bonn are analyzing the occurrence of rare filament structures using high-order correlation functions, clustering statistics, and extreme value theory. Early results indicate a 5-6 sigma deviation from standard WCDM predictions based on Gaussian initial density fluctuations, prompting further investigation of alternative initial conditions, including mild non-Gaussianity and inflationary perturbation variations. Observational cosmologists are collaborating with particle physicists and high-energy theorists to examine whether novel dark matter candidates, early dark energy, or modifications to general relativity could contribute to the formation of filaments. Workshops at CERN, the Kavli Institute, and the Perimeter Institute are exploring scenarios where multiple non-standard processes act together to produce rare structures while remaining consistent with constraints from the cosmic microwave background, baryon acoustic oscillations, and supernova observations. JWST enables time-domain studies of galaxies in filaments. By observing multiple fields at different epochs, astronomers measure star formation rates, mergers, and AGN activity across hundreds of millions of years. Early observations show that some filament galaxies have reduced star formation compared to field galaxies. Teams at MIT, University of Toronto, and Durham University are combining these observations with machine learning classification of galaxy properties to analyze environmental effects. Surveys are targeting fields across multiple redshifts to build a statistical sample of rare, massive structures, including filaments and protoclusters. JWST, Roman, Euclid, and ALMA are mapping the cosmic web from Z is approximately equal to 2 to Z is approximately equal to 6. These observations quantify the occurrence of filaments, measure the range of galaxy properties within them, and provide data to compare with cosmological simulations. Researchers are expanding observational metrics beyond galaxy counts and stellar masses to include gas fractions, metallicity gradients, halo occupation, galaxy alignments, and filament angular momentum. International teams at institutions including the University of Cambridge, Princeton, Max Planck, and Tsinghua University are coordinating to standardize these measurements, enabling direct comparison between observations and simulations. Each new dataset, generated by JWST, contributes to an evolving narrative about the extremes of the early universe. Filaments like the one discovered challenge our assumptions, stimulate theoretical innovation, and drive the next generation of surveys. By integrating multi-wavelength observations, high-resolution simulations, and advanced statistical analyses, astronomers are gradually constructing a more detailed and nuanced picture of how rare, massive structures emerge, evolve, and influence the galaxies within them. In doing so, the JWST filament is not merely a singular object, but a gateway to an era where cosmology must confront the unexpected in the early universe.